Hey, good day, everyone. We're going to discuss geometric sequence today. So let's take a look at the objectives of this lesson. Number one, illustrate geometric sequence. Second, we have to differentiate a geometric sequence from an arithmetic sequence. And finally, we have the third objective, determine geometric means and the nth term of a geometric sequence. So let's take a look at that. So take a look at the first scenario that we have here. In this particular problem or in this particular scenario, we have a certain culture of bacteria doubles every 4 hours. If there are 50 bacteria at 7 a.m., how many bacteria would there be at 7 a.m. the following day? So clearly, this particular problem or particular scenario investigating what will be the number or what could be the possible number of bacteria after how many hours or from 7 a.m. this day and then the following day. So that's what we're going to investigate here. So let us analyze the problem by making a list showing the growth of the bacteria. We will just look at the growth of the bacteria here. Day 1 starting 7 a.m. It is stated in the problem that we have 50 or there are 50 bacteria. Now, so the growth, as you can see in the given, you can see that the bacteria doubles every 4 hours. This is very essential. Take note. Doubles every 4 hours. So every 4 hours is constant. So as you can see, 7 a.m. plus 4, it becomes 11 a.m. and then plus 4, it becomes 3 p.m. then 7 p.m. then 11 p.m. And then after that, of course, that's already 3 a.m. the following day. And then another 4 hours, it is 7 a.m. So now, as you can see in the list, we have from 7 a.m. down to 7 a.m. the following day. So at the start, we have 50. The number of bacteria is 50. And then after 4 hours, we have the bacteria doubles the number. Okay, so 50 times 2 equals 100. And then 3 p.m. it becomes 100 times 2. So that becomes 200 now. And then another 4 hours, it becomes 200 times 2. It doubles again. So it becomes 400. And then another 4 hours, 400 now times 2, which becomes 800. And then comes the following day, another 4 hours. So 800 times 2 equals 1,600. And 7 a.m. the following day, 16 times 2, that's 3,200. So now the problem, if you look at the problem, let's go back to the problem. How many bacteria would there be at 7 a.m. the following day? So here it is, we answered already that the number of bacteria 7 a.m. the following day is 3,200 bacteria. So this could be a process that you can do by listing, but of course it will be tedious. It will be requires more work if you're asked to, let's say, up to day 10. You will not be doing that listing. Will be a very hard task, a very tiring task for you to do it if you're gonna list that down. But let's discover a very essential way or method by using a formula on how we're gonna solve this one easily. Okay, so taking a look again at the list that we did from day 1, 7 a.m. to day 2, 7 a.m. So let's analyze. The growth of the bacteria forms a sequence that can be written as 100, 200, 400, 800, 1,600, and 3,200. So as you can see, looking closely at it, taking a note at the sequence that we form here, the difference between any two consecutive terms is not constant. So look 100 to 200, the difference is 100. And from 200 to 400, the difference is 200. And from 400 to 800, the difference is 400. And from 800 to 1,600, it becomes 800. And finally, from 16,232 is 1,600. So if you closely look at the difference here, we can see that we don't have a constant difference. Unlike in an arithmetic, it has a constant difference. Okay? So this is something that we should take note of when you are going to differentiate an arithmetic from a geometric. Okay. Now, thus, this is not an example, of course, of an arithmetic sequence. The example that I have here, this is not an example of an arithmetic because as you can see clearly that there's no common difference. So, by examining the pattern that we have here, as you can see, also, the operation that we use is not anymore addition or subtraction, but instead multiplication. So, it's time I move to look for the succeeding term or from previous element to the second element. Each time I move or I look for it, I just multiply it by 2. So in the illustration that we see above, the succeeding term is obtained by multiplying the preceding term by a fixed number, which is 2. So this kind of sequence is called geometric sequence, or sometimes it is called as geometric progression. So the fixed number rather is called the common ratio, and we denote that as R. So again, the common number that we multiplied here, as you can see, times 2, times 2, times 2, and so on. So that's the common number that we multiplied here, or the fixed number, and we call that as the common ratio. And we denote that, we write that as R. It is obtained by dividing the succeeding term by the preceding term. Succeeding term, 200. This is the succeeding, and the preceding is 100. So 200 divided by 100, that's going to be our process. So in short, we're going to have this formula, a sub n plus 1 all over a sub n. Simply, because this one is a sub n, this one is a sub n, this is a sub n, this is a sub n plus 1, increasing in term, because this should be a1, a sub 2. Okay? Now, so in simple terms, this is s over p, succeeding term over the preceding, or succeeding over the previous term. You can have it check. You can check it by dividing 1,600 by 800 or 3,200 by 1/6. And if you have the same number, the ratio is the same, then it is a geometric sequence. Okay, again, the process is division. So division, it involves division here in finding the common ratio. So the common ratio involves division. While in the arithmetic sequence, as we previously discussed, arithmetic sequence, to find for the common difference, we just subtract the succeeding term minus the preceding term. That's the process here. So that's the differences that we take note of when it comes to arithmetic sequence and geometric sequence. Let me give you an example, another example of a geometric sequence. Say, for example, 3, we have 3, 9, and we have 27, and we have 81. And then that, meaning to say this is an infinite geometric sequence. So this is an example, infinite geometric sequence, because there is an ellipsis here. So let's take a look and determine the common ratio. How do we determine the common ratio here? So we will determine the common ratio here by dividing the second term by the first, or the succeeding term by the preceding term. So again, the common ratio is simply denoted as R, which is equal to succeeding term over the previous or the preceding term. So here, as we can see, this is our A1, A sub 2, A sub 3, and A sub 4, or element 1, element 2, element 3, and element 4. Now, the element on the second term, or element number 2 is 9. You divide it by 3, by the previous, it becomes now 3. So it should be all throughout. When you try to check 27 by 9, it should be common. The common ratio is 3, or 81 by 27, still it should be 3. Otherwise, if it is not common, when you try to divide each of the succeeding over the previous term or the preceding term, then it is not a geometric sequence. Okay, so now, if you're going to look for the succeeding or the next term, we can just multiply 81 by 3 since we know already the pattern. So this is our pattern, multiply by 3, because this is our common ratio. So this could be, if you look for A sub 5, since we don't have the A sub 5, A sub 5 will just be simple. We will just multiply 81 by 3, and now you have 243. Or if you look for A sub 6, you can just go on and multiply again 243 by 3, since that is our common ratio. So multiplying this by 3, we have 9, and then we have 3 times 4 is 12, carry 1, so 2 times 3 and plus the carry 1 is 7, 7 to 9. So this will be the terms that we can have after multiplying it by 3. So of course, you can look for the succeeding terms again, 7 to 9 times 3, and so on. All right, so that's how simple it is when we look for the common ratio, and that common ratio will be utilized in order for us to find the succeeding term. So let's say you gonna look for again the other term, the 7th term, the 8th term, and the 9th term, and so on. Now, let's continue and have another example. Let me just erase a bit here. Okay. This is a bit simple. Now, if you look at the process that we did in the situation, we just repeated the process that we have there. All right, so let's have another example here. Another example that I will be giving is this one. So let's say, for example, we have 40, 20, 10, and 20, and 5, 40, 10, or 20 rather. This is 20, 10, and 5. And then that. So this is again an example of an infinite geometric sequence. Why? Because we don't know the last term here. We don't know what will be the last number. But we have our A sub 1, the first term, our A sub 2, the second term, A sub 3, the third term, and A sub 4, the fourth term. Now, what will be our common ratio? So the common ratio that we have here is S over P, succeeding over the previous. So 20 divided by 40, it's going to be 1/2. Okay, you just cancel this one, 0, and then 2 over 4 is 1/2. So therefore, our common ratio is 1/2. Now, if I look for the fifth term, I will just multiply 5 by 1/2. And this will be 5 times 1 is 5, and then just copy the denominator 2. So therefore, this will be our fifth term. If you wish to look for the A sub 6 or the succeeding terms, you will just multiply each time by 1/2. So 5 halves, this time we have 5 halves because since this is our fifth term times 1 half. So now we have 5 times 1, and then we have 2 times 2. So simply, if we simplify that, we have 5 over 4. So that's how we look for the succeeding term in geometric sequence. So take a look at the procedure. It's just a simple one. And let's say, for example, you are asked to find the 30th term or the 20th term of this particular sequence. There is a formula that we're going to be using here. And the formula that you should take note of will be this. A sub n, or geometric rather, A sub n is equal to A sub 1 times, this is an asterisk multiplication symbol, r raised to n minus 1. So this is our formula for finding the term that you wish to look for. Let's say, for example, we want to look for the 10th term of this given geometric sequence. Now, if we used to look for, if you wish to look for that 10th term, let me just put it here. So here, find the 10th term. So we will just use the formula again. The formula is A sub n is equal to A sub 1 times the ratio, the common ratio, raised to n minus 1. So since we're looking for the 10th term, so we are looking for the 10th term, we will change n here by 10. And then we have A sub 1. As you can see, our A sub 1 is 40. And then we multiply it by the common ratio. Our common ratio is here, is 1 half. That's 1 half. Raised to n minus 1. Our n is 10 minus 1. So our A sub 10 now is going to be 40. If we continue the process, times 1 half raised to 9. Okay. Now, if you look for that, if you solve for 1 half raised to 9, if you have your calculator, maybe you can do your the procedure by multiplying it 1 half 9 times. But of course, it will be tedious. So you can work for it using your calculator. You can solve for it. And that is going to be 1 half. You're right, 1 half raised to. So that is 1 half first. You're going to multiply 1 half times, raised to 9 rather. 1 half raised to 9. So what would that be? Okay, that is 1 half raised to 9 is equal to 1 over 512. So it will be 40 times 1 over 512. So if you multiply this one, simplify, that is 5 over 64. So therefore, our A sub 10 is going to be 5 over 64.